Okay, we're going to go through practice exam A. I'm going to just start on question one and kind of work through. You have the answer key with some of it worked out, but I'll show you kind of draw some additional pictures, so show you some additional things like I could have changed or I could ask, and really kind of walk through it, right? Unless we have any specific questions that we want to start out with, I'll just start out with question one. So I can kind of see the chat here. If you put a question there, I can start with that one. Otherwise, I'll probably just start from question one. Slight delay, so wait. Okay. Um, so we've got the first one, and just like the first exam, the practice exams, it's going to be a very similar format in terms of the flow. Now, obviously, these are going to be up, the exam's going to be on Canvas as opposed to like a physical copy in front of you. But I'm still going to keep it kind of short or multiple choice, and maybe one short answer at the end, which I'll talk more about when we get to the kind of later questions. So this very first question, we're told the waiting time at the BMV is uniformly distributed from 0 to 60. Okay, so I've got this random variable x. It's uniformly distributed, minimum of 0, maximum of 60. Okay, so I want the mean or expected value of this distribution. What would I do? Okay, so I've got my formula sheet here. If I look at these four equations here, these are going to be my uniform distribution equations. Okay, so this tells me the height, right? Remember C and D. C is the minimum, D is the maximum. So if you have this in front of you, and you're going to have a formula sheet, you can download this and use it as you're working through the exam on Canvas. D is your maximum, C is your minimum. So to find the mean or expected value, you would add the two values together and divide by 2, right? You're just looking for the middle value, okay? So if we think about what this looks like visually, there we go. I drew this ahead of time. But right, you've got your maximum, your minimum. The expected value is, I'm just looking for the middle of these two numbers. How do I find the middle of two numbers? Well, I add them up and divide by 2. All right, so 60 plus 0 divided by 2 gives us that mean of 30. The next question is, what is the variance? So I have kind of that written out right here. But where does that come from? If we go to the formula sheet, our variance for the uniform distribution is take the range, right, maximum minus the minimum, right? So maximum minus the minimum, square that, and then divide by 12, right? That gives you your variance. Right? So that's what I did here. Maximum minus the minimum, square that, divide by 12, that's your variance. If I wanted the standard deviation, I have to do one more thing, which is simply take the square root. Right? So the next question asks, what's the probability that you wait more than 35 minutes? Right? So here, it helps to have drawn out what a uniform distribution looks like. Excuse me. So I have this drawn out, this rectangle that starts at 0, ends at 60. Right? So if I want the probability it's greater than 35, I forgot to label it here, right? But there would be a 35 right here. So the probability it's greater than 35. Well, if the mean is 30, I know the area to the right of the mean should be 0.5, right? The mean should exactly split that distribution in half. And so if the mean is 30, the area to the right of 30 would be 0.5. Then the area to the right of 35 is something less than that. So if we look at even our potential options here, we actually can rule all of them out except for A. All right? So, I mean, just knowing like that the mean, there's 0.5 to the left and the right, and that we're looking for the probability being more than 35, automatically we should rule out B, C, and D. But how do we exactly get A, just in case we couldn't rule out every other answer? Excuse me. Well, what do I want here? I want my formula sheet. This is kind of the equation that we can use. So it's B minus A. B and A are the end and beginning of my interval. D and C were the maximum and minimum. I think it's easier to think about it this way. If we look at this drawing, the height of my distribution is 1 over the range, or 1 divided by the maximum minus the minimum. So 1 over max minus min. Once I know the height, well, what would be the length of my interval? Well, I'm going from 35 to 60. So what's the gap, or what's the difference between those two? 60 minus 35, or B minus A. Take that base of my rectangle, look at the height of my rectangle, which was 1 over 60 here, multiply those two, and I would have the area of this rectangle. And this should be 0.41, and it's like 0.41666 repeated. So I rounded that. Okay. So it's as simple as that, right? Base of my rectangle, we always know the height of the uniform distribution is 1 over max minus the min. So it's not too bad to get that. Okay. Similar for 4, very similar kind of idea. It's just now I'm looking for the probability between 15 and 20. So my height is still the same, but now instead of going from 60 to 35, I'm just going from 20 to 15. Right? So that was very similar, just kind of a different range. Okay. And so what, 5 times 1 over 60 should be 0.0833 there for 4. So those two we would solve very similarly. Okay. All right. So the next one, number 5, we've got now a random variable x, but it's normally distributed from 37, and kind of just before we move on, really you should expect to see questions similar to this with a uniform distribution. I would practice on the second exam as well, because when this isn't 0, it's a little bit trickier. Maybe go back to the Connect homework. One of these was negative. It makes it a little bit more difficult as well. But just get some more practice there. I would kind of go back to those connect questions where you have a negative one, or practice exam B. Okay? And of course, I could ask you for the standard deviation, so the variance. That's just taking the square root. But these ones could ask you questions like these. So now I get this random variable x on 5. It's normally distributed. The mean is 3,700. The variance is 250,000. Right? So what's the probability that it's greater than 3,000? Okay. Well, if you think about what this is going to look like in terms of the picture, got one right here. Okay. Oh, and I want to zoom in. Okay. So I've got this mean. First of all, the variable itself is normally distributed, so I drew that out. It's got a mean of 3,700, and I want the probability that it's 3,000 or greater, right? So it's shaded in the area to the right. Well, if I've got a normal distribution, I know that I don't want to do that integration. I can use a standard normal table if I convert this value I'm interested in into a z-score, right? Into a standard normal distribution. So how would I do that? Well, if I look at this formula sheet, go down here, when I'm just dealing with a variable, I haven't sampled from a distribution, I'm just looking at the distribution itself, I'll take that x value I'm interested in as the cutoff, I'll subtract the mean and divide by the standard deviation. That gives me my z-score, right? This guy right here. So I take that x value of 3,000, I subtract the mean of 3,700, I divide by the standard deviation, which I cheated here a little bit because I did the intermediate step first. So I was given the variance was 250,000. I know I want the standard deviation here, so how do I find the standard deviation? Well, it's just the square root of the variance. So I took the square root here, that was 500. Why did I write 250 here? I don't know why I did that, so I apologize. I was doing this quickly before I got on here. It should be 500, right? And then when you do this math, the denominator should be 500 here, and it would give you negative 1.4. Okay. So this should be 500, because that was the standard deviation. So we've got negative 1.4 is my z-score. I want the area to the right, but when I go to the table and I look up that negative 1.4, so I go negative 1.40, right, because the second decimal is 0, negative 1.40. The area to the left of that is 0.0808. So this area is 0.0808. I want the area to the right. Well, if the area under the curve is 1, then I would just subtract this from 1, and it would give me the area to the right. So 1 minus 0.0808, 0.9192. Okay? And if I drew this out, and I'm thinking about this, what should the area to the right of the mean be? 0.5. So what would the area to the right of something to the left of the mean be? Well, that area includes this and this area of 0.5, so it has to be greater than 0.5. Right? So I look here, what are the only possible options I could see? Well, B, C, and D, but why could I rule out D? Well, we're looking for a probability, it has to be between 0 and 1. Right? So, and if I'm choosing between B and C, I'm looking at a value, like in order for the area to the right to be close, this close to 0.5, I'd have to be looking at a value that was really close to that mean, right? And 300 is pretty far away, okay? Especially if we look at how many standard deviations away. It's more than one standard deviation. Right? All right, so 6 is going to be very similar. Now we want the probability that it's less than 3,200 or greater than 4,200. Okay? So I think, let me double check here on the answer. This one might be the, because we have, oh no, okay. So we've got less than 3,200 or greater than 4,200. If I wanted to do this one, oh, all right, we'll zoom in. Okay. So I think originally, I don't think I have completed this one because I had the question a little bit wrong, but if I want the probability it's less than 3,200 or greater than 4,200, I could do this multiple ways, right? I could find the area that's in the middle here in between them and then subtract that from 1 and I'd be left with what's in the tails, right? So what I have here is how we would find that. So I would first turn 32 and 4,200 into z-scores. And actually, I'll go to drum this one out. Just so I think I did a little bit incomplete there, so we'll just get a drawing of it. So if I've got this guy here, and I just said the mean's 3,700, what's the probability it's greater than 4,200 and less than 3,200? Well, if I think about how would I turn these into z-scores, right? The equation we have is take the mean, actually we're not dealing with sampling, we're just dealing with the data. Sorry about that. We'll take that value we're interested in, subtract the mean, divide by the standard deviation. Right? The standard deviation we had up here was the square root of 250,000 or 500. Right? So 3,200 minus 3,700 over 500 equals negative. I apologize for that. Okay. We're getting the UPS man or something. Hey, he's fine. Hey, Lapua. Alright, sorry about that. So we've got here, might have to edit that out. We turned this into a z-score, which was -1. Notice, we don't even have to do the rest of the work for 4,200 because how far away is 3,200 from 3,700? 500. How far away is 3,700 from 4,200? 500 as well. So this was one standard deviation below. Well, that was 500 below. So if this is 500 above, that would be one standard deviation above. So the definition of our z-scores helped us there because we remember it's the number of standard deviations away from that mean we are. So we're now looking for this area. We can look up that z-score of -1 on the table. Find it's 0.1587. We can then look up the z-score of 1 in the table. The problem is it's going to give us the area to the left, which is 0.8413, I think. We wanted the area to the right, so we would have to do 1 minus that. But also notice, I don't even have to look this up. Remember, this is a symmetric distribution, so if the area to the left of -1 is 0.1587, the area to the right of +1 would be that same 0.1587. So if I find this tail, I automatically do this one. So I could add them up or multiply this by 2, and I'd get my final answer. Now in the answer key, I showed you a different way of doing it, which is if these weren't the exact same, you could have found the area that's in between them, and then, like if I found this area, then to find the area in the tails, I could have subtracted that from 1, right? So there's multiple ways to do this one. All of them will lead you to the same answer, which is like, what, 0.3 something that we've got there that you can see in the answer key. Okay? All right. So now we'll move on to 7. Okay. All right, so suppose we've got a random sample of 25 people. What would the mean and standard deviation be, right? So we're sampling from this variable up above of calorie consumption. If we sample 25 people and we look at the sample mean, what should the distribution of those sample means be, and what would the standard deviation of those sample means be? Well, if we look at our formula sheet, here's kind of our sample means. See the variances and standard deviations here. Now I don't have it written down here, but we've talked in length about for our sample means, they should always be normally distributed if the original data was normally distributed, or we have a sample size over 30. So this one, I'm not trying to trick you here. I'll usually give you a variable that started out as normally distributed, so even if we don't have a sample size of 30, we're okay there, right? But if we started out with, say, the uniform distribution, in order for the sample means to be normally distributed, I would need to have a sample size over 30 for that central limit theorem to be met. Right? So I know the mean of my sample means should just be the mean of the original data I sampled from. Right? So that'd be 3,700. So B or C here we know has to be the answer now. Now the standard deviation, if we look at that formula sheet, well, it doesn't really help us. It's the square root of the variance over the sample size, right? So this guy right here. So we look at the original variance of 250,000, divide that by 25, and then take the square root. Right? So if I do that, I think I had it right here. Up here. So if I do that, I should get 100. Okay? So I've got this standard deviation of 100. I know the mean of my sample means is 3,700. Right? So I could draw that out. But here I don't have to draw it out, I just have to select the one that is. So here we're going to be going with C. Right? So this is very important. This is one part where I've tried writing these before where I give you some assumed true values at this point, but it always kind of ends up being more confusing. So number 7 is going to be crucial that you understand how to find the mean and the standard deviation of your sample means, because you're going to have to use those values kind of moving forward, right, for number 8 and 9. So this is the one part of the exam where this would have, the questions would be somewhat linked together, okay? So we've got our mean, we've got our standard deviation. What's the probability that 20 of these 25 people I sampled, the average calorie consumption I find is less than 3,550? Well, if I go to drawing where I drew this, okay, I draw this out. I know the distribution of my sample means will be normally distributed, since the original variable I sampled from was normally distributed. Has a mean of 3,700, and I want the probability is less than 3,550. So I want the area to the left here. Well, I know that I have to turn this normal distribution into a standard normal distribution, or z-scores. So 3,550, how do I turn that into a z-score? I have the kind of written down here, but as a reminder, if we look at the z-score, up here, this is how we find the z-score for sample means and sample portions. Well, we have a sample mean, so we'll take the sample mean value we're interested in, that cutoff, we'll subtract our mean, and we'll divide by the square root of our variance over our sample size. Well, I was given all that in the problem, right? So I took my sample mean value I was interested in, subtracted the mean, divided by the square root of the original variance over the sample size, or this denominator represents dividing by that standard deviation of my sample means. Okay? So if I'd already found this ahead of time, I could have just plugged 100 here in the denominator, But if I plug in all the parts, I'd still get 100, so it's okay. So I get this z-score, and it's kind of faint here, you can't quite see. It's not negative 15, it's negative 1.5. So I then look up in my standard normal table, negative 1.50, the area to the left is 0.0668, and that's my answer. Okay. So 8 would be A then. Okay. So then for 9, right, it's going to be very similar, but we have a little bit more work to do. We still are interested in certain values of the sample mean, but now with the probability that it's what? Greater than 3,500 and less than 3,700. So I go ahead, I draw this out. So I want the probability that's between 3,500 and 3,700. Well, 3,700 is my mean, so this actually makes this one a little bit easy. Because what should the z-score for that mean be? Z-score should be 0, and the area to the left, excuse me, of that mean, area to the left and right should always be 0.5. So I know the area to the left here is 0.5. But I have to subtract out this area to the left of 3,500 in order to get the area in between. Okay? So I turn 3,500 into a z-score. 3,500 was the value I'm interested in. Subtract the mean, divide by square root of the original variance of the data I sampled from divided by the sample size. I get a z-score of negative 2. So I go ahead, I look that up in the table, negative 2.00, 0.0228, 0.0228, subtract that from 0.5, and that gives me the area in between, which is what I wanted, which should be 0.4772. Now if I look at this, and I think about which ones I could have ruled out here, well notice, if I know the area to the left of the mean is 0.5, and I want the area that's in between these two values, I know it's something less than 0.5. So right away when I looked at this, I should have been thinking A, B, or D. I could have ruled out C right away. Okay. All right. So that was kind of some of the older stuff, and that was stuff that we had probably, we had definitely covered prior to us going online. So the rest of this I'll probably do, I don't have it kind of drawn out ahead of time, I'll do it on the board. I also think it's good for you to just see me work through more of these on the board, some of the newer stuff, right? Okay, let me double check something here too. Okay, so for number 10, I've got this random variable P. It indicates the kind of population proportion of what? NCAA athletic programs that generate positive profits. So I take a sample of 400 NCAA teams and I find 55% have a positive profit amount or a sample proportion of 0.55. Okay. Now, one thing I could have done here is told you, there we go. One thing I could have done is said, not directly told you what that proportion was. I could have told you that 22 of the 40 schools that I sampled from had a positive profit amount. Well, if I tell you that, right, 22 out of 40, how could I find my sample proportion? Well, right, it's just the number of successes, whatever I'm looking for is my success, divided by the total number I sampled, right? And that would give me that sample proportion of 0.55. So I might not directly give you what that is like I did in this problem, but as long as I tell you this many out of this many, you can find the sample proportion. Okay? So, somehow I got scrolled down here. So I've got that sample proportion of 0.55. I want to do a 95% confidence interval about where that true population proportion is. Okay? So first of all, you can go to our formula sheet. I've got my 3 confidence interval equations right here. So I'm looking at a sample mean, and I know what the original, or no, sorry, I'm not looking at a sample mean. I'm looking at a sample proportion. All right, made a mistake there. So I'm looking at the sample proportion. So this is the one that I'm going to use. Right? All I need is my sample proportion, which I just said was 0.55, my sample size, which was 40 schools, and now all I have to do is find what the z-score is. Okay? So it kind of reminds me, all right, you got to find the z-score that gives you alpha over 2 on either side of the confidence interval. So my alpha would be what? Well, the 95% confidence interval, alpha I said is kind of the area outside the interval, but in decimal form. So 5% is outside, decimal form, that's 0.05. That's the easiest way to remember. So alpha is 0.05. I'll divide that by 2, right? So 0.025. I go to my z table, because if I'm looking at a proportion, sample proportion, I use the z or standard normal distribution. So I look up the area I want in the tail, which those are the areas in the middle, right? The numbers in the middle represent the areas that I'm looking for in the tail. So I want 0.025. What's closest to that? Oh, it's actually right here. Negative 1.96. Now, if we look at this confidence interval equation, if I look up alpha over 2, I'm always going to find a negative value because we're looking at small alpha values. So I don't want the negative in here. That's kind of already built into my confidence interval, right? Negative 1.96, that's going 1.96 standard deviations below the sample proportion to build the lower bound. I would then want to go 1.96 standard deviations above the sample proportion to find my upper bound, right? I'll add my margin of error to get the upper bound, subtract the margin of error to get the lower bound, okay? So I've got everything I need. It's just a matter of plugging everything in, right? So if you look at here, I'm not going to kind of work through this one. You've got the kind of answer here that really just does exactly what I said, right? We found that z value of 1.96. I plug that in, plug in my sample proportion of 0.55, plug in my sample size. This is really just a matter of being able to kind of use that calculator, use your calculator correctly once you have everything plugged in. Okay? So that one shouldn't be too bad. The next question, right? Using the same information, right? So this is, use this for the next 5 questions. So use this with this, use this information to kind of keep going. Okay? So I've got what? I'm kind of cut off here. So Forbes reports that 45% of the programs have a positive profit amount. You want to test the hypothesis that the true population proportion is something different than 45%. Right? So anytime we see this word or term or phrase, different than, you should be thinking that there's a not equal to sign in your alternative hypothesis. Different than means you just want to know, is it any other value than 0.45? So what we're testing for is that it's different or not equal to 0.45, which means we'll assume that it's equal to 0.45. Okay? So the next couple of questions, I'm just going to kind of answer by drawing on the board, but we're looking for the test statistic, we're looking for critical values, and then we'll kind of, I'll use some assumed true values here, but using these, I'll determine whether or not we can reject or not, right? So I go to my formula sheet. I've got 3 equations for test statistics, right? Here is one where I'm looking at sample proportions, so I'm going to use this one, right? If I'm looking at proportions, standard normal or z-tables, right? So I've got my sample proportion I found of 0.55. The value I'm assuming it was equal to was this 0.45. And my sample size was I had 40 schools. So once I have that, plug those values in, pretty easy to get my test statistic there. Okay? So with this in mind, I'm going to kind of draw this one out. All right, so we've got, let me see if we can go here. Okay. 0.45, no, sorry, 0.55 was what the sample proportion found. We assumed it was 0.45. Divide by the standard or square root of 0.45 times 1 minus 0.45 divided by 40, which was my sample size. Right. Remember, this kind of represents that standard deviation of my sample proportion. So I could have found the intermediate step and then plugged that in. I could calculate this first and then plug that into the denominator. But once I do that, and you think about, I have a 2-tailed test. Right? So once I put this into my calculator, I think I've got, and I can actually do this here real quick in front of you, so I don't have to. 0.1 divided by the square root of 0.45 times 0.55 divided by 40. So 1.27, if I'm doing this right. So we found a z-value of 1.27. But for a two-tailed test, for every value we saw up here that went against the null, it would have been equally as likely we saw something that was the same distance away from that assumed true proportion, but in the opposite direction. So we can find the area of this tail, but for a two-tailed test, we have to remember, oh yeah, I have to multiply that by 2 in order to get my p-value, right? So each side with a two-tailed test really only represents half of my p-value, okay? So I could look up 1.27. It would tell me the area to the left of it. I would then subtract that from 1. Once I have that, I then multiply it by 2 to find my final p-value. Right? So if I do that, all right, let me double check that I then could have made a mistake because I was trying to. Yeah, so 1.27. We'll look that up. We're dealing with a proportion, so we use the standard normal distribution. So 1.2. Go all the way over to 7, so 1.2, 0.898. Right? I would then subtract that from 1, so what? 0.102. That was only one of my tails. Right? So that was just, this tail was 0.1020. So I need this times 2, 1020, or 0.204, right? So, oh, that's not what I want. We'll go right here. All right, so I've got my test statistic, 1.27. Oh, and actually, I gave you an assumed true test statistic for later on, but if we wanted to find the p-value for that one, that's what we would have done. Right? Later on, I give you an assumed true just in case you got 12 wrong. I tell you, assume it was 1.34. Well, then what would you do? It would be the exact same thing. Right? You'd want to find the area to the right of 1.34 and then multiply it by 2. So I'm guessing if we do that, right, 1.34, so 0.9099. So we subtract that from 1. Right, so 1 minus 0.9099, we get 0.0901, but that's not our p-value. That's only half of our p-value, so we multiply that by 2. 0.1802 is our total p-value. Do we reject or fail to reject? So we only reject, and this is, you should, I don't know, burn this in your memory. I usually joke and say get tattooed before this exam. Right? So we only reject if the p-value is less than alpha. So we just found a p-value of like 0.18. Is that going to be less than an alpha of 0.1? 0.18, is that less than 0.1? No, it's not. So instead of rejecting, if it's not less than, we would fail to reject. Okay. Oh, and I'm typing a bunch of stuff in this Word document on accident. Okay, so we did a test statistic, we've done p-values here. How would I find my critical values? Okay, well, critical values are going to be the cutoff values that give me desired amounts of alpha in my tail, if it's a one-tailed test, or in my tails, if it's a two-tailed test. So here we have a two-tailed test, so it's going to be what values would give me 0.1, 0.05, and 0.01 combined in my tails. Right? So I'll draw this first alpha of 0.1. That's kind of where we'll start out. Right? So if we want to find these critical values, right, we're thinking about, got this standard normal distribution, because I'm dealing with sample proportions. Oops. So if I've got an alpha of 0.1, then I've got alpha over 2 in each tail if it's a two-tailed test. So 0.1 over 2 or 0.05. So what value or values here, one will be negative, one will be positive, would give me 0.05 in that tail? Well, if I know the area that I want in the tail, I can just look that up and I could find what this value would be from my standard normal distribution. So I go in the middle of that table, I find the one that's close to 0.05, and it's in between 1.64 or negative 1.64 and negative 1.65. I'll take the higher of the two, or if I take that out to the third decimal, which I can get from the last row of the student t distribution. Remember we said that last row where it has degrees of freedom infinity would also be the values you'd find from the standard normal distribution. We'll get that negative 1.645, but at any given alpha, we actually have, kind of right, those two critical values, and here they should be the same value, so negative and positive 1.645. Now once we look up 1, notice if we look at this answer key, once we find that first one, we know that there's pairs. We could look up the other two as well, but once I identify the first one, I can identify what is the correct set of critical values here. So 1.645, if I look up an alpha over 2, so 0.05 divided by 2, which was 0.025, I'll find 1.96. And if I divide 0.01 by 2, 0.005, I look it up in the table, I'll find 2.58. So the way I found that, I kind of explained the process. But when I wanted 0.05 in that lower tail, I looked in the middle here for what was closest to 0.05. It looks like it's these two, in between negative 1.64 and negative 1.65. Okay? Or I could go to that last row on my student t distribution, which I said represented the standard normal values you'd find. So the area I wanted in the tail was 0.05, so 1.645. Okay? So I've got my three critical values there as well, or my three pairs of critical values for a two-tailed test. So automatically, once you identify that it's a two-tailed test, because you have that not equal to sign in your null or alternative hypothesis, you know it has to be either A or C. If it was a right-tailed test, we should have positive critical values, and if it was a left-tailed test, we should have negative critical values. Right? So we'll work through an example that's a left or right-tailed test here in a second, not with proportions, but with a slightly different type. Okay, where are we at in time? We're doing good. Haven't seen any questions come in. I thought when I checked earlier we had a couple people watching, so hopefully watching this live is helpful. If you have any questions anytime, like I said, please feel free to type something in the chat and kind of interrupt. So I'll just double check that's even working. Test. Okay, it's working. So we've got this next example, which we'll use for the remainder of the questions, I believe, with the exception of 21. Let's say I survey 30. Oh, I have a question. So when is the test? So the actual exam, I'm going to get it posted on the 31st, and I'll kind of put in there how long you have to do it. My kind of an idea is that it'll be due by the end of the day Thursday, so you'll have a good almost 72-hour time period, probably a little less. I'll post it, release it in the morning, or maybe I'll have it set so I'll just have it set so it releases at midnight, kind of Monday night. So you'll have all of Tuesday, all of Wednesday, and all of Thursday. You can take it at any point during that time block. I mean, once you take it though, you can only take it one time. So once you start it, there will be a time limit on it, probably pretty long time limit, kind of depending. Don't have it completely written into Canvas yet. My guess is you'll have about an hour and a half to 2 hours to take it, depending on how many questions I end up putting on there. So anytime during that 3-day time block, you can take it. You can download the formula sheet. You'll have a lot more resources available to you than you usually do. So I may make it a little bit longer, a few more questions, make it a little bit a bit tougher, but it should be pretty comparable to what these practice exams are. Okay, so that was a good question. Um, any other questions? Otherwise, we'll kind of go back. Or maybe he was just trying to make a joke saying, when is this test? Since I typed test into the chat. But nonetheless, that's good. We got that out of the way. And I'll put an announcement on Canvas about that as well. So for this next one, we survey 30 dentists. We find an average salary or a sample mean of 145,000 and a sample standard deviation of 10,000. So we don't know what the true population mean or variance is, and we want to construct a 90% confidence interval. So anytime we're dealing with sample means, and we only have a sample variance or a sample standard deviation, that's when we should be thinking about, we need to be using that student t-distribution. Okay? So I have a sample mean, but I only have a sample standard deviation, or I only have a sample variance. Okay? So right away, how do I construct this confidence interval? Well, it should be pretty easy. If I go to my formula sheet, I have a sample mean, but I only have the sample variance, so this is the one that I'm going to be using. And it even reminds me, yeah, hey, don't use the z tables, use those t tables now. Okay? So this is what the equation I'm using. I have my sample mean value, I was told. I don't have the variance, I have the standard deviation. So I'll plug in just for S, what was it? That 10,000 for S. I have my sample size to plug in. So the only really tough part of these confidence intervals is looking up this value, this either z or t value, in this case a t value. So it reminds me my degrees of freedom is simply n minus 1. So if I look at this, I've got what? 30 dentists. So my degrees of freedom would be 30 minus 1, or 29. My alpha for the 90% confidence interval, so what's outside the interval? 10%. In decimal form, 0.1, so my alpha is 0.1. So the area I want in the tail, right, in each tail is not 0.1. That's the total area in the tails, but it gets split in half. So the area in each tail is 0.1 over 2, or 0.05. Okay? So I go to my table, my student t table. I know the area I want in the tail is 0.05. That was my alpha over 2. And then I go down to my degrees of freedom of 29. The value that would give me that desired alpha in each of my tails, 1.699. Okay? So now that I've got, oops, I didn't mean to do that, sorry. Now that I've got that t value, it's just a matter of plugging everything in. Okay? So kind of in the answer key here, right, I'm just plugging everything in. Now, once I find that t value, the other thing that's kind of important is my standard deviation, right? I only have the standard deviation, so I still have to square that 10,000, right? Because what's in that numerator there is the variance. I only have the standard deviation, but if I have the standard deviation, how do I get a variance? Well, I just square that value. So I subtract that marginal area at the lower bound, I add it to get the upper bound, and there I'm done. Right? I can, with 90% confidence, say the true starting salary of a dentist is somewhere between about $142,000 and $148,000. Right? I don't know what value in that range it is, but I know with 90% confidence it's one of those values. Okay? All right, so the next question is, suppose that some article is published saying that the average salary is $150,000. You want to test for whether or not the true average salary is less than that amount. So you want to test for whether or not it's less than that amount of $150,000. That's your alternative hypothesis. So we go down here. I want to know, is it less than $150,000? Now here, one thing I kind of mentioned in the lectures is the value in your null or alternative hypothesis is something that you are kind of testing for or against. It's not what you found in your sample. So 145,000 here shouldn't make sense to us. We should be thinking B or D, and we only would answer D if it said, is it different than, right? So we're testing for, is it less than, so less than 150,000 is our alternative hypothesis. We'll assume the opposite is true, which is that it's greater than or equal to, and see if we can find evidence that kind of goes against the null enough to reject it or not. Right? So what would my critical values for this be? Well, first of all, if I've identified it's a left-tailed test, and here, one thing I'll do in Canvas is, like, I might ask you to identify the null alternative, and then I'll give you, assume that it's this. right? That way we're all starting off in the same, because if I got this one wrong, I potentially could get the critical values wrong as well. Because the critical values for a left-tailed test should be what? Well, left tail, so if I'm thinking about what this looks like visually, if I'm looking at the left tail, and I want to find critical values, well now I'm dealing with a student t-distribution. It still looks like a normal distribution, just a little, variance is a little bit wider. So I want the critical value that gives me, to start out with, we'll say 0.1 in that left tail. With a one-tail test, we don't have to divide alpha between two tails, it's all in one tail. So what value, what t value would be the cutoff that would give me 0.1 in that lower left tail? Right? So I go to my table and I say, well look, I know that I want 0.1 in that lower left tail. Now the problem with the student t-table is it's kind of telling you the upper right tail, but it doesn't matter, right? It's a symmetric distribution. So if I'm finding the cutoff value that gives me 0.1 in the upper right tail, the same value but negative would give me 0.1 in the lower left tail. So it'll give me the value, and I just have to remember, oh yeah, it's a left-tailed test. These critical values should be negative. Right? So, and the reason why they're, right, if I'm thinking about they're to the left, what's true about what's the mean of my student t-distribution? Well, it's just like the standard normal. The mean is 0. So if I want a small area, an area less than 0.5, this critical value has to be kind of negative. Okay. Oh, there we go. So I want 0.1 in that tail. My degrees of freedom was, well, this is still when we were at 30 dentists, so 29. I wanted 0.1 in the tail, so negative 1.311, right, left tail test, so negative 1.311. And then the next alpha was, I wanted 0.05 in the tail, so same degrees of freedom, so negative 1.311, negative 1.699, and then the area of 0.01 in the tail, at degrees of freedom 29, negative 2.46. So those would be my critical values, right? So these three values right here, right? I should have been able to rule B and D out right away once I knew it was a left-tailed test. Oh, and there we go. Because I know for a left-tailed test the critical values have to be negative, so B and D I should be able to rule out pretty quickly. Okay. How do I find the test statistic for this test? Above test? Well, if I go to my formula sheet, here's my test statistics. I'm looking at a sample mean, but I only have the sample variance, or I only have the sample standard deviation. So it's really just a matter of identifying which test statistic I need to use, and I can do that because I only have a sample variance and I'm looking at a sample mean. So it's this guy right here. So now it's just a matter of, I won't write this one out, it's pretty easy. Just a matter of plugging those values in, right? Here's my sample mean, here's the assumed true mean, here's my standard deviation, here's my sample size. So I get this test statistic of negative 2.74. Right. Now, if you got that wrong, you would most definitely get 19 wrong. So how could I find kind of whether or not I reject or fail to reject? Well, I need my critical values, I need my test statistic. So this is where I said in the test, I won't ask you to find a p-value for the student t-distribution unless I give you an assumed true test statistic that you could find in the table. So first I'll show you the critical value approach here, and then I'll show you an example if I did ask you for the p-value approach, how I would have had to do it here. So I've got this test statistic of negative 1.5. Really what I'm going to do is, all right, I'm going to plot my critical values, and then I'm going to plot where my test statistic will fall. Okay. I'm going to drop my marker cap. So I've got this guy here. Let's see if I can remember these values. I might not. So this is what, negative 1.311, negative 1.699, and negative 2.4 something. My rejection regions would be the areas for a left-tailed test to the left of those critical values. Okay. So I give you then an assumed true test statistic in problem 19 of negative 1.5. So where would that be? Right here. So it's in the rejection region for my alpha of 0.1 or 90% level, confidence level. It's not in my rejection region for an alpha of 0.05 or my 95%, and it's definitely not in the rejection region for that alpha of 0.01 or my 99% level. So the only one that I can reject that is the 90%, and then I fail to reject at the 90 and 95% levels. Okay, so there would just be that 10% level. Right? And like I said, I'll usually give you an assumed true test statistic there, because if you got the test statistic wrong, well, how do you plot that against the critical values, right? Okay. And I could also, this is where I might do a short answer where I ask you to work through whether or not it's the critical value or the p-value approach. I ask you to work through a problem and really ultimately arrive at that rejection decision. Now, in order to do that, I've kind of walked you through it here, but you'd first have to identify the null and alternative hypothesis. You then have to identify critical values. You then have to calculate your test statistic. You then have to like plot them and determine whether or not you reject or fail to reject, right? But that would be the kind of short answer I'd ask, is basically to work through a hypothesis testing problem. Okay. So if I wanted to ask you for a p-value here, I wouldn't give you a test statistic of negative 1.5. I'd have to give you, or I wouldn't have to, but what I'm not going to do anything other than give you one of the values that you would find here. I would ultimately give you one of these as, so I might say, assume the test statistic was negative 2.045, right? What would the p-value be? Well, you want the area to the left of negative 2.045, so that'd be the area, same as the area to the right of positive 2.5. At that degrees of freedom of 29, you would go up and go, okay, the p-value would then be 0.025. But it's very, I'm more likely to ask you for p-values when you have to use that standard normal distribution, because there we can look things up a little more accurately. Here, there's just not as many values. Right? I kind of mentioned this when we did in the lectures and when I went to Excel. In Excel we can find the p-value of any value for the student t, but we're somewhat limited here with just this table. Okay, so instead of 30 dentists, you had found the mean and standard deviation from 60, which of the following would be true? So this one's kind of tough, but if you think about what's going to happen, right, with each one of these changes, we should be able to understand which of them would make it more or less likely that we would reject the null. Okay, so the very first one is the new test statistic is smaller than before. Okay? Well, let's think about what that would do. So let's say, that marker is not working. It's not what we're going to say, but. Alright, so let's say I've got some, we'll do a right-tailed test here so I can kind of show you an example of that. Let's say my critical value is right here, and here's my test statistic. What happens if, like A said, that test statistic is smaller? Well, if it's smaller than before, it could potentially go from where, right, this was my rejection region, so I could go from rejecting, if my new test statistic is smaller, I could then fail to reject. So that makes it less likely I reject, right? So here I'm looking for, oh, sorry, that was not A. C was that we would be more likely to reject the null. Well, this actually shows us, no, we would actually be less likely to kind of, oh wait, oh, hold on, I'm explaining this wrong to you. No, I mean, this part is right, but I think I have it reversed. We're going from 30 to 60. So, here we go. Assume true value. Okay. So this was my test statistic equation, right? If instead of 30 here, I go to 60, what's going to happen? Well, if this denominator goes up, this whole thing gets smaller. If I'm dividing by a smaller number, then my test statistic ultimately would go up, right? So if n goes up, my test statistic would also go up. And that's the reason why, is because finding the same exact value, but with a higher sample size, remember that the higher sample size reduces the variance. right? This guy represents the standard deviation or the variance, or the standard deviation, so it reduces the standard deviation variance of those sample means. So seeing the same value is now going to be a larger number of standard deviations away from that assumed true value. So higher sample size will lead to a higher test statistic. So I had this backwards where, let's say originally we started out, so here's my critical value. Let's say originally I started out with a test statistic over here. With a higher sample size, I know that's going to push my test statistic up, making it more likely I reject. Right? So in 20, we're looking for which one would be true. We're more likely to reject before. The test statistic is going to be higher. We're more likely to reject the null. And what would have to be true about the p-value? Well, remember, the p-value is the area to the right for a right-tailed test. So if my test statistic gets larger here, I'll use a different color. If my test statistic is getting larger and moving to the right, potentially now my p-value is just this blue area, or my p-value is smaller, right? So if I take a higher sample size, my test statistic gets larger in absolute value. My p-value gets smaller, and if my p-value is smaller, so I was kind of using the critical value approach to show you that we'd be more likely. But remember, if my p-value is smaller, it's more likely to be less than alpha, in which case we're more likely to reject. Right? So if we're looking there, the only one I think that was true, right? So we had a larger test statistic, so A wasn't true. We had a smaller p-value, so B wasn't true, and we would be more likely to reject the null than before. So C was our answer there. Okay. All right, we got one more to work through, and we'll kind of wrap things up here. So I suppose that I've got Ball State students who are in state, approximately 87%, and the variance of blah, blah, blah. We take a sample of 100 Econ 221 students and find that the proportion of them that are in state is 0.81. Right? So I know the population proportion, and I now have a sample proportion. Right? If I'm trying to figure out, suppose we take a sample. Okay. So should we be using the student tier standard normal distribution if we're trying to figure out a test statistic or perform a hypothesis test or build confidence intervals for an example like this? Well, anytime, it doesn't matter if they give you the population variance here, we can always calculate that, right? If we knew what the population proportion is, we could always calculate the population variance. Anytime we're dealing with a proportion, we can use the standard normal distribution because we're looking at proportions, right? It doesn't matter if we're given the variance or not, because remember, the equation that we had for, let's say, there we go, right? As long as I know, if I did know the population proportion, right, I automatically, it's built into my standard deviation of those sample proportions. So as long as I know it, I'm always gonna know the population variance when I'm dealing with a proportion example. And that's really the reason why, for proportions, we can always use that standard normal distribution, right? So we're always going to be able to use, I deleted something here. We're always going to be able to use that standard normal distribution because we're dealing with sample proportions, okay? All right, so that's practice exam A, kind of working through it, adding in some additional things that I could ask you. I would say the beginning part of the exam on Canvas will look very similar, the first 10 questions, or 9 or 10, will look very similar to the two practice exam questions. From there, it's really confidence intervals and hypothesis testing, which has been the stuff that's been online. So it's not ideal that I think it's the harder stuff, and that's what we've had to do online. But hopefully this has helped. You have the lecture slides, or the recorded lectures to kind of review with. And outside of doing the two practice exams, I put up a practice problem set, which is not for credit. You don't have to do it. It looks like it's another Connect homework. I tried to make it very obvious it's just practice. I even labeled it practice problems. So if you want some more practice doing hypothesis testing and building confidence intervals, please go on Canvas and work through those. After you do that, I would maybe go back through the recorded lectures and you can look at those iClicker or example problems I worked through. Make sure you know how to solve each one of them. After you do that, that should have you pretty prepared. Like I said, it's going to be a multiple choice exam just like the first one. I will have kind of a short answer portion at the very end, which I'll already tell you. I'm not telling you what type of hypothesis test problem it will be, but we have three, right? Sample mean, where I know the population variance, sample proportion. So both of those, we use the standard normal distribution. And then the third type is when I have a sample mean, but I only have the sample variance, right? Or only have the sample standard deviation, in which I use the student t-distribution. So I'll ask you one of those, like a complete problem of here's what you want to test, identify the null alternative hypothesis, calculate the test statistic, use either the p-value or critical value approach to make a rejection decision, right? So I'll grade those with some partial credit, but I may ask you to do that. And if I do have a short answer portion there, I haven't played around too much with that on Canvas yet. I may set that up so you can kind of have a file upload. So if it's easier for you to, like, instead of type it on the computer, you can write it on some paper, take a picture, and upload that. Right? So that short answer portion, might be more like a kind of a take home, where the multiple choice portion you have a set number of time, and then I kind of give you this short answer problem where you upload it on Canvas. Right? But I'll put an announcement with more details once I have that actual exam built into Canvas. I've done this before for an online course in terms of putting an exam up there, so hopefully it doesn't take me too long, and I should have an announcement out either today or sometime this weekend. Okay? All right, we'll end the recording there.